we have one more talk by Maurice, and the title is ZK Promises, Anonymous Moderation, Reputation, and Blocking from Anonymous Credentials with Callbacks. Please go ahead.
Yeah, I'm happy to be back. I was a software engineer here at Microsoft, so it's nice to be back on campus. Yeah. So my name is Maurice, and today I'm really excited to talk about ZK Promises and an anonymous credential scheme with callbacks. This allows for negative feedback, like downvotes or banning, in a way that users cannot avoid without needing to know who they are or de-anonymizing them. Researchers have spent since about at least 2007 on this problem, and we not only build the first practical and efficient scheme, but we allow for a much more expressive system by making clients run arbitrary functions with integrity guarantees. This means that you can program any logic you want, such as an anonymous payment scheme with ratings, reputation, and risk scores. So let's go through a use case. So anonymously editing Wikipedia. We have Wikipedia, a centralized server, and an anonymous user who wishes to make edits on Wikipedia. Wikipedia wants to support this in order to protect the privacy of their users, but they still want to be able to punish those who misbehave, even if they don't know who they are. So for now, let's assume that for the sake of exposition and to describe the functionality, that the user will honestly follow our protocol, but they will still try to vandalize the page if possible. So we call these clients honest but obnoxious, and later on we'll show how cryptography removes this honesty assumption. So we have this anonymous user. They make this malicious post, in this case a rickroll, and they submit it as edit. Later on, they may try to make a second edit. But since the first edit was a malicious one, we need a system where Wikipedia can block all future actions of this user after this malicious edit. So the first building block is that we use random tags, denoted in these orange boxes. And these are associated with each action. So then each action has its own random tag. And the user will store these random tags. And the servers will use this association between the action and a tag to ban or punish offensive edits. So how this works is we have a public ban board, as shown below. And the anonymous user, who's set in this honest but obnoxious mode, will scan through all their tags of prior posts. And as long as none of these tags are on this public ban board hosted by Wikipedia, then they're allowed to edit. They're not banned. So after this first offensive malicious rickroll, Wikipedia will post the number 12 to this ban board. So then when this anonymous user tries to go to make a second edit, they'll check through all their tags of prior posts and sees that 12 is posted. This means that they're banned, and this honest user will now recognize they're banned and not make any other future posts. And to do this, the client needs to have some sort of state to record all the tags of prior posts. So we have this user object here on the left. For now, it has a list of posts it made. And because we have this user object, we can also now add in this bool denoting whether this user is banned or not. And when it scans through all these tags, and if it sees one, it'll modify this bool, this single bit is banned. And we can see that this system of tags, these random numbers, is actually an asynchronous callback. And in this example, a form of asynchronous negative feedback. And we can do a lot more. This is actually much more powerful than just editing a single bit on the user object. We can have some arbitrary data in this user object. And this callback can be just more than just the random number tag. It can be any arbitrary function with arguments that can mutate the program data in this user object. So this user object plus callback model is very powerful and allows for a lot of complex logic. So it could do a three-try expand system, a reputation system, or even some crazy Web3 credit scoring system. Not that I recommend you do that, but it is possible with this system. But all of this works on the assumption still that the client is honest but obnoxious. And this honesty assumption is obviously not realistic. So our next step is we want to shift away from this model to a malicious security model. In particular, we need to prove that there's correct state transition done on this user object. We need to make sure that the user can't roll back to some prior state after making some spicy edits. And we have to make sure that the client will process all callbacks correctly. And we want to do this all while keeping this user anonymous. And in this case of user objects, we have to hide which user object is being updated. So a great first approach is zero-knowledge proofs. They're very powerful, and we'll be using them. As a quick crash course, a zero-knowledge proof allows a prover P to prove some statement to a verifier that some statement is true without revealing additional information. And while these are very powerful and we are going to be using them, ZK proofs alone are not enough. So the idea of random tags plus zero-knowledge proofs have actually been explored in prior work, such as Black and Pereira. And they have limitations because they only rely on ZK proofs. So in the case of Black, the ban list is a nonce and tag. And a client has to prove for every single entry in the ban list that the PRF evaluation of their key and that nonce is not equal to the tag. Basically, this pair is not generated by them. So a client has to do work per element in the ban list. So this can not scale well. The follow-up work by the same group is counter-based. So there's this public constant n, and a client has to prove that on a PRF evaluation of the user key and a counter from 0 to n, none of these outputs are in the ban list. So then client authentication now is O of n work. And this O of n is needed because n is the maximum actions a client can do within a certain time period. So this both limits how much actions a client can do, and it forces all users to do worst case authentication. So both of these systems have their own drawbacks. And they have these drawbacks because ZK proofs don't keep state. When you try to prove state transition from state Si to Si plus 1, nothing prevents you from doing Si to Si plus 2, getting rid of that prior state. So without state, we cannot support also reputation or other complex programs, and they're concretely inefficient as shown in these prior two works, as clients have to iterate through all possible posts they could have made. As a side note, works such as Snarkblock and Alpaca do stateful ban lists. So we now introduce something we call the ZK object model. This lets ZK proofs keep state using a server or blockchain. And this has a reformulation of techniques in Zcash and Zexy. And how this works is for each state transition from Si to Si plus 1, we reveal the nullifier of the prior state, which is a random tag. And as long as the server keeps track of all seen nullifiers, then the replaying and forking cannot happen. So let's look at how ZK objects work. We still are in the same scenario of a server, an anonymous user. The anonymous user will have this user object stored locally, and they can prove valid state transitions using this function prove. So how this works is the client will prove that they know a valid signature on a commitment. This means that the user state is a valid one signed by the server. It will then open up this commitment to the user object and a nullifier, apply some method and functions to mutate this user object, pick a new nullifier, and then make a commitment to the new user object nullifier. It'll create a ZK proof, send it over to the server, along with the new commitment and old nullifier. And on receiving this, the server will first verify that the ZK proof is valid, check to see that the nullifier has not been seen before, add that nullifier to the seen list. And now, since all these checks have passed, it means it was a valid state transition from a previous valid state. So everything checks out. So then it'll sign on the new commitment, showing that it's valid, and then send it back to the user. So this is a very powerful scheme because it allows anonymous users to prove states without revealing anything about themselves, and then mutating it to some new state. So with this model, we can now let dishonest clients keep state because they can't mutate it in a way that's not allowed. As a side note, my slides are mostly on the centralized setting, but nothing prevents you from doing it in a decentralized setting like a blockchain, where we, instead of doing signatures, we do Merkle tree membership proofs instead. So these ZK objects are very, very powerful, but unfortunately, as is, there are some limitations. They're very powerful since clients can anonymously prove statements about their state. They can also modify their state only as programmed, so they no longer have to be trusted to be honest. But in its current state, there is no way for a third party, such as a server, to alter the user state. So they can still be obnoxious, make bad posts, make bad edits, and still get away with it. So this is where asynchronous callbacks come in. I mentioned before, this notion of these random tags. So as a quick refresher from what I spoke about, this is just, callbacks is just the method where you check through all the tags of your prior actions. And if a callback has been uploaded, then you apply that to your user object. In ZK objects, we can do the same exact thing. We call this the process of looking through all the tags called scanning. And we can use this as a method onto the ZK object and with the same logic as before. And the user must scan recent enough in order for their state to be considered valid. And in this way, the users can never evade negative feedback, negative callbacks. They will must eventually accept it and process it. So a bit of engineering question is how do we verify if a callback has been called or not and has been posted? So a naive way is to have a marketized key value store for all possible callbacks. And this is very inefficient in ZK proof since it would require 256 hashes per lookup, something that's way too expensive. So instead, we split the data structure into two, one of the called callbacks and one where it contains the ranges of callbacks which have not been called on. And by doing this way, each tree only has to be around 32 hashes, something that is much more efficient. So for this given public callback board, this is an example of the two data structures. So these are two Merkle trees. One is a key value store, and one is the empty key value store. And to check for membership, it's very simple. So for a callback that's not been uploaded, you would find the leaf where it contains the interval, and then prove membership. Likewise, for callbacks that have been called, you find a leaf where the key is that of the tag, and then prove membership of that. So since one tree path is only checked a single time, a callback is either called or not. It cannot be in both. Only one membership path needs to be checked in the ZK proof, which makes it more efficient. And on the server side, these data structures are very efficient to update, since these leaves do not have to be sorted. So insertion only takes in O of log n time, since no rebuilding or sorting is required for these. And a limitation of this ZK object model is that these two trees will always grow because they're append only. So periodically, old states can be pruned to limit the growth of these trees. What this means is every single user object has to have been updated in, let's say, a year. And if they're not, then they're considered no longer to be valid. A second method to limit the growth is to have epoch-based trees. So then this is a way of segregating different trees by different year or whatever time set you want to make the system a little more efficient. And in the centralized setting where we have signatures, we can have signatures that are over the commitment and some expiry time. So then after a certain amount of time, these signatures will be considered invalid. So another thing is callback expiry. As this user object works, as defined, this my tags list will grow indefinitely. As you make more callbacks, they keep adding and adding, and we never remove anything from the list. So this cannot scale well. This is not practical for the user. So to fix this, we set that each callback is single use and is removed after processing a callback on the callback board. And also there's an expiry to remove them. So the server has, let's say, 1 week to moderate and post a callback if it deems it needs to make an action. So each callback now needs an upload time, a simple and small modification. And this expiry time can be something fixed, so let's say a week, or something by the caller's choice. This is system designer's choice. And something very similar to this is callback scan frequency. How often does the user object need to scan for these callbacks to be considered valid? So this is a trade-off between how up-to-date the user object can be versus how much work the server and client needs to do. So there's the eager scenario where before every authentication, the user has to scan for callbacks. So then that ensures that it's the most up-to-date state. Or the lazy where after a callback expired, check to see if any callback was uploaded. Yeah, so this is a system designer's choice since it's more computational load versus more how up-to-date you want. And it's not only a computational load, but each scan requires interaction with the server. So it's also a network and how much bandwidth the servers can handle, not just on the client side. But we do have follow-up work that does reduce the need for server interaction per scan. Yeah. Another piece of note is that is Sybil resistance. How do we defend against this? So the system as described works if users can't make new accounts. If they can't make new accounts, they have to accept the punishments and update their user object. But that's not realistic. What prevents them from just making a new account in the real world? Well, this is inherent to any system, and anonymous or not, and we can't prevent them from doing so. But due to the programmability of these user objects, we can make new accounts a lot less useful. We can require that in order for a user account to be useful, it needs to have a certain age, it needs a certain amount of reputation or anything else to make it so it's much, much harder for new accounts to be used for abuse. And a very similar note is avoiding punishment. After a banning callback is uploaded, what if the user just never processes it and goes offline? Well, we can't prevent this. Nothing prevents this at all. This system does not guard against that. Only future continued interactions are dependent on them accepting this punishment. So this is one limitation because we can't force banned users to reveal something about themselves. We can't make them de-anonymize them or something like that. Yeah, so that's, yeah. So, yeah.
I have a question about the leakage of this. Like you mentioned that there's a public callback board that I'm seeing. I think it might leak something. I'm not sure. That's why I'm going to ask if it leaks something. And you also mentioned for the Sybil resilience, to rely on account age and reputation. Don't they also leak? Like, is there any analysis of that, or is it not a threat?
So it's, yeah, that would be a leak. So it could be that like your account has to be at least 1 week old to make an edit. That is a requirement. So then implicitly, anytime there's a valid authentication, that account is older than a week. Yeah, all of this would be the parameters are all public.
What do you mean with the reputation? How do you define it? Is there any?
Any logic you can design is implementable. So it could be like you're rate limited to 1 post a day until you gain a certain amount of reputation, and then you get it. You're allowed to do more posts in 1 day.
And the board doesn't, the callback board doesn't leak any information with this post-true things where they don't?
So that is an excellent question. As is the system, the protocol designed, does leak it. So then when you make an authentication, you would, as part of the public input of the ZK proof, you'd be like, this callback is 72. And then when the Wikipedia server uploads this callback with ID 72, you know that there is correlation because you can see it. So we do have them, it's not explained here, but in our paper we do describe that you can hide it. So instead of revealing the tag, you would reveal a hash of the tag and a nonce. And then when you send that proof to the server, you would reveal the nonce to them, and they can check that the hash of a tag and that nonce is equal to that. And that way there's no linkability.
The burden is on the user side, right?
Yes. Yeah. But excellent insight. That's exactly one problem.
You have a question of expressivity. Is there a way to provide programming logic that involves multiple objects? Can you, in terms of expressiveness on the programmability, can you have some callbacks involve multiple objects, or do a read request for an object before updating another object? Or is everything limited to a single object at a time?
Sorry, I couldn't really understand your accent.
Sorry, let's try again. So, in terms of expressiveness, you describe an arbitrary logic that concerns the state of a single object I'm wondering if it's possible to extend that logic to talk about the state of other objects, like reading the state of some objects and updating a single object, for example.
Okay, so like if you wanted to like read multiple client objects for
Yes,
something.
yes, yes.
That is current future work that we're working on. So if you have ideas or want to talk about that, I am very excited to talk to you about it.
Okay, let's talk, yes. Thanks.
Yeah. So to help support that, we support arbitrary logic. We have implemented this very complicated logic on the right in Rust with ArcWorks, both in the centralized and decentralized setting. So some example of things that we implemented was a multi-dimensional weighted reputation, a leaky bucket rate limiting based on that reputation, callback spiral logic, and much more. And all this was hand-coded. There was no compiler toolchain that we could use. And we ran benchmarks to show that this is actually pretty practical. Even with all this complex logic, client authorization is only about 300 to 400 milliseconds. A single callback scan is around 400 to 600 milliseconds. And the server verification is around 2.8 milliseconds, or with batched is 0.7. And with Wikipedia's numbers, US Wikipedia, we show that this is actually pretty reasonable times. I don't think anyone can make an edit in less than half a second. And then follow-up work uses folding to batch scans. And this reduces the time required for a single scan to about 150 amortized. So in conclusion, we created ZK Promises, an anonymous credential scheme with callbacks. It uses the ZK object model to make dishonest clients run stateful programs. We use callbacks to allow asynchronous negative feedback that they cannot evade. And we do all of this while preserving client anonymity. This can be used in many things, such as forum pseudonyms, Tor bridges, and risk scoring of cryptocurrency addresses. And I'm very excited to see where this system can be applied to and future work to improve on this. Thank you.
Okay. Any more questions?
Did you talk to Wikipedia?
So for the callback Merkle trees that are created by the server, is there any authentication that goes into the server creating those callback trees?
Yes.
Correct?
Yeah. So if you don't have any authentication, the client, since they know the callback ID, could immediately post something. And since they're single use, then the server would never be able to post something. So an extension is the callback ID, instead of being a random tag, will be a public key, a re-randomized public key that the server sends over. So then when a callback is uploaded, you check to see if the callback signature validates using that public key.
Did you talk to Wikipedia or any other domain that your application, your solutions might be applicable to?
Yeah, so we talked to someone who worked at Wikipedia to grab the numbers of the rate of usage and also like reversion rates to see how many callbacks would need to be uploaded.
Any more questions? Awesome. Well, let's thank Maurice again.